In 2009, at the Hessentag Festival in Germany, engineers from the Hessian Energy Saving Action tested a reconstructed Bronze Age wall. The results shocked them. This 3,400-year-old design matched building codes from 1995. But here's what stunned them most. Between the Bronze Age and 1995, we got 4 to 6 times worse at insulation. We didn't forget, we regressed. Picture a medieval peasant, January 1320, outside -40 degrees Fahrenheit, no electricity, no heating system. He's warm. Cut power to your modern house for 24 hours in that cold? Pipes freeze, walls crack. What did medieval peasants know that we forgot? Today, 7 inventions that kept peasants alive in winters that would kill us in days. Drop a comment. What's the coldest temperature you've experienced? Let's begin. Invention 1. Heat storage hypocausts. The heat storage hypocausts. A heating system so efficient that modern technology still can't match its fundamental principle. You've probably heard of Roman hypocausts. Underfloor heating in bathhouses, hot air circulating beneath raised floors. Impressive, yes, but the Romans had a critical flaw: constant fire required. Feed wood into the furnace all day, every day. Fire dies, heat dies with it. Medieval monks in northern Europe faced winters where -20, -30, even -40-degree temperatures were common. The Roman system was too inefficient, too expensive, required too much labor and fuel. Around the 14th century, possibly earlier, medieval engineers made a breakthrough that changed everything. They added thermal mass, massive granite boulders. Here's the complete system. Dig a chamber beneath your floor. Build a barrel vault furnace using stone or brick. Stack granite stones, each 16 to 20 inches in diameter, on top of that vault. These weren't random rocks. They were specifically granite for its thermal properties. The room above featured a perforated hot plate, essentially a floor with strategically placed holes. Critical detail: these holes stayed closed during the burning phase. The operation was brilliant in its simplicity. Light your fire once, let it burn hot and fast for 2 to 4 hours. The flames and hot gases heat those massive granite stones to temperatures exceeding 500 degrees Fahrenheit. The stones absorb this thermal energy, storing it in their crystalline structure. When the fire completes its burn and you've cleaned out the ash, close the smoke flue to trap the heat. Open the vents in the floor. Physics takes over. Hot air rises from the superheated stone pile through the floor vents into the living space above. But this isn't a quick burst. The granite stones, now functioning as a thermal battery, release heat slowly and steadily. For 3 days, 4 days, 5 days, sometimes longer. A single firing, warming your entire living space for nearly a week. Think about the mathematics here. If you're burning fire for 3 hours every 5 days, that's roughly 36 minutes of active burning per day averaged out. Compare that to a modern furnace cycling on and off every hour, running perhaps 6 to 8 hours total daily in deep winter. The medieval system required maybe 10% of the fuel consumption for comparable results. The system spread rapidly across northern Europe. By the end of the 15th century, historians estimate 800 to 1,000 heat storage hypocausts existed in the Baltic region alone. They appeared in monasteries, where monks needed reliable heat for copying manuscripts, in castles where nobility demanded comfort, in town halls and guild halls serving public functions, even in private homes of wealthy merchants. But here's something remarkable. This was convective heating, not radiant. The Roman system heated floors, which then radiated warmth. The medieval system actively moved hot air through convection currents, a more efficient heat distribution method. Modern heating engineers didn't understand this technology until recent decades. Through the 1980s and into the 90s, standard histories claimed Roman heating technology was mostly lost after the empire collapsed. They had no idea. Medieval builders not only preserved the knowledge but dramatically improved it. Now compare to your modern home. Your natural gas furnace or electric heat pump runs constantly throughout winter. Natural gas flowing, electricity consumed non-stop. Monthly heating bills in cold climates easily reach $400, $500, even $600. The medieval peasant with access to a heat storage hypocaust. 1 load of firewood every 5 days. If wood cost money, it was a tiny fraction of modern heating costs. If you gathered your own, it was free except for labour. This represents something profound about technological philosophy. Modern systems prioritise convenience. We want heat now at the flip of a switch. We've built infrastructure requiring constant energy input to maintain constant comfort. Medieval systems prioritised efficiency. Work hard once, benefit for days, use thermal mass intelligently, respect the principle that captured heat should be stored, not continuously generated. Which approach makes more sense in a world facing energy constraints? Invention 2. Lanolin-treated wool to... From heating buildings, we move to heating the body, and here medieval peasants possessed technology that baffles modern material scientists. Fabric that becomes warmer when it gets wet. Sounds impossible. In 2015, a research team attempted developing synthetic fabrics that could generate heat upon moisture exposure. The project failed. The chemical reactions required were too complex, too unstable for manufactured materials. Medieval peasants accomplished this accidentally, through sheep husbandry. The science is fascinating. Sheep produced lanolin, a waxy yellow substance secreted by sebaceous glands. Lanolin coats wool fibers naturally, serving multiple functions, protecting the sheep's skin, regulating moisture, providing water resistance. When you shear a sheep, the raw fleece contains roughly 12 to 25% lanolin by weight. That greasy, almost sticky feeling of raw wool, pure lanolin. Modern textile manufacturing removes it entirely. We wash fleeces with industrial detergents and hot water in a process called scouring. Why? Because consumers want wool that looks clean, feels soft against skin, and doesn't smell like sheep. So we strip away the lanolin completely, often selling it separately to cosmetics companies for use in lotions and creams. Medieval peasants couldn't afford such waste. More importantly, they discovered through generations of experience that lanolin-rich wool had properties bordering on miraculous for cold weather survival. 3 key properties made this revolutionary. First property, natural water resistance. Lanolin creates a waxy barrier that repels liquid water. When rain hits properly treated wool clothing, water beads form on the surface and roll off rather than soaking in. Not completely waterproof like modern Gore-Tex, but water-resistant enough that you could work outdoors in light rain or snow for hours without getting dangerously wet. For medieval peasants who spent entire days outside tending livestock, harvesting crops or performing manual labor, this was survival critical. Second property, moisture absorption without saturation. This seems paradoxical with the first property, but wool fiber structure explains it. Wool can absorb up to 30% of its own weight in moisture vapor before feeling wet to the touch. The fiber structure has scales that channel water preferentially toward the garment's hem. This means moisture collects at the bottom edge where it can drip away, while the upper portions of the garment closest to your core body remain relatively dry. You could sweat heavily inside wool clothing or have snow melting against it, and the garment maintained insulation properties. Third property, and this is where it becomes almost magical. Wet wool generates heat. Not perceptually, not metaphorically, actually measurably, chemically generates thermal energy. Here's the mechanism. The outer surface of wool fiber, called the epicuticle, has microscopic pores. When environmental humidity is high, these pores actively draw in moisture vapor from surrounding air. Water molecules enter the fiber core through these pores. Inside the fiber, water molecules encounter the complex protein structure of keratin, the primary component of wool. A chemical reaction occurs. The hydrogen bonds in H2O molecules break apart. These broken hydrogen bonds then form new chemical bonds with the amino acid chains in the wool protein. This bond formation is an exothermic reaction, meaning it releases energy in the form of heat. Modern laboratory tests confirm this. When wool absorbs significant moisture, temperatures in the fabric can increase by several degrees. Not a huge amount, but in survival situations every degree matters. When you're already on the edge of hypothermia, a few degrees of additional warmth can be literally life-saving. Compare this to cotton, humanity's other major natural fiber. When cotton gets wet, it conducts heat away from your body 150 times faster than when dry. Wet cotton clothing accelerates hypothermia. This is why experienced outdoors people have a saying, "Cotton kills." Synthetic fabrics. Most of them lose their insulating air-trapping capacity completely when saturated. Polyester fleece, when soaked, provides almost zero warmth. Nylon the same. But medieval wool? It continued functioning, actually improved performance in wet conditions. Medieval peasants built their entire cold weather survival strategy around wool. They understood layering long before modern outdoor education programs taught it. Innermost layer, linen shirt or chemise against skin. Linen wicks moisture away from skin surface through capillary action. Next layer, wool tunic or coat. Then another wool tunic, then a thick wool cloak. Total thickness could easily be 4 to 6 inches of layered wool. For legs, they wore woolhosen, basically fitted leggings. In extreme cold, 2 or even 3 pairs of hosen layered together. Wool hats covering ears and neck. Wool mittens, often with separate outer mittens for double protection. Every garment wool. It worked. Medieval chronicles and records describe people working outdoors through brutal winters, temperatures well below freezing, without the frostbite injuries or hypothermia deaths we'd expect. They understood intuitively what modern science has since confirmed. Wool is the king of cold weather survival fabrics. Modern outdoor industry is slowly, reluctantly, rediscovering this ancient wisdom. Merino wool base layers now command premium prices, $50 to $100 for a single shirt. Wool socks, wool mid-layers, wool outer garments, all marketed as high-tech solutions. The lanolin, most manufacturers still remove it, though a few specialty companies now advertise raw wool or lanolin-rich products at 3 to 4 times the cost of regular wool. Medieval peasants had this superior technology as their default, everyday clothing. What we sell as premium outdoor gear, they considered basic necessity. Invention 3. Wattle and Daub. Double wall. The same 2009 German reconstruction that opened this video revealed something that should humble every modern builder. The Bronze Age wall's thermal performance. U factor between 0.5 and 1.0 watts per square meter, Kelvin. For context, that matches German heat protection regulations from 1995. This design was 3,400 years old. The testing engineer published findings with a remarkable statement, quote, "We should very humbly acknowledge that comparable high insulation values were not reached again until the heat protection regulation of 1995. In the thousands of years in between, the insulation grew 4 to 6 times worse with timber-framed houses, 3 times worse with solid brick walls." Translation: for over 3 millennia, human civilization regressed in thermal building performance. We didn't maintain standards. We got dramatically worse. The superior technology that we forgot and then relearned. Double-walled wattle and daub construction. Let's understand what this means. Basic wattle and daub is simple in concept. Create a woven lattice of thin, flexible wooden branches called wattle. Think basket weaving applied to walls. Then cover this lattice with daub, a mixture of wet soil, clay, animal dung, and straw or other fibrous material. The daub dries hard, creating a solid if somewhat irregular wall surface. That's the simple version used in many cultures. One wattle layer with daub applied to both sides. Decent weather protection, moderate insulation, but nothing exceptional thermally. The advanced version developed in Bronze Age and maintained through medieval times used 2 parallel wattle layers with a critical insulating cavity between them. Construction process worked like this. First, build your primary wattle panel. Vertical staves driven into the ground or secured to the building frame. Horizontal withies, typically willow branches woven between the staves. This creates a flexible but stable lattice. Apply daub to the exterior face, building up layers until you have a weather-resistant surface, perhaps 1 to 2 inches thick. Now the crucial step. Instead of daubing the interior face immediately, construct a second wattle panel parallel to the first, leaving a gap of 4 to 8 inches, depending on climate severity. Northern climates used wider gaps. Fill this cavity with dried grass, not loose grass, but densely packed. This is critical. The grass needed tight packing to prevent air circulation while maintaining its structure. Proper grass packing created millions of tiny air pockets, each too small for convective air currents. Air, when still, is one of nature's best insulators. Its thermal conductivity is extremely low. The challenge is keeping air immobile, If air can circulate, convection rapidly transfers heat. The grass matrix solved this beautifully. Each blade of grass divided the cavity into microscopic still air chambers. Perfect insulation using the most abundant material imaginable. After packing the grass cavity, apply daub to the interior wattle, completing your wall sandwich, exterior daub, wattle, grass cavity, wattle, interior daub. The sophistication here is remarkable. Both daub layers provided thermal mass, absorbing heat during day and releasing it slowly at night. The grass cavity provided the actual insulation barrier, preventing heat transfer. And because all materials were naturally porous and breathable, moisture could gradually migrate through the wall without accumulating, preventing rot and mold. Wall thickness varied by climate. Moderate regions like southern England might use 4-inch cavities. Harsher northern areas like Scandinavia or northern Germany used 6 to 8 inches or more. Some archaeological finds suggest cavities as wide as 12 inches in the coldest regions. The materials were locally sourced and essentially free. Willow or hazel branches for wattle grew abundantly near streams and wetlands. Grass covered every field. Clay came from the ground beneath your feet. Straw was harvest waste. Animal dung was, well, animal waste. Zero material cost. Labour-intensive, yes. Building a complete wattle and daub house required community effort. But materials, free. Compare this to modern insulation technology. Fiberglass bats manufactured in factories from melted glass fibers. Foam board insulation made from petroleum-derived polymers. Spray foam requiring specialized equipment and chemical expertise. All these products require industrial manufacturing, chemical processing, energy-intensive production, and of course money. Lots of money. A modern home's insulation package can easily cost $10,000 to $20,000. Medieval peasants built comparable or superior thermal performance from materials they gathered themselves. But here's the tragic irony. Despite having this proven technology for millennia, we abandoned it. Why? Partly because we could. Industrial materials seemed more modern, more advanced. We built thinner walls because we could engineer buildings differently. We prioritized construction speed and cost over thermal performance. We assumed technological progress meant abandoning old methods. Only in 1995, after decades of energy crises, after computer modeling, after modern building science matured, did we finally achieve thermal standards that Bronze Age builders had mastered with grass and mud. Medieval peasants maintaining this tradition understood something we're only now relearning. The simplest solution, using the most basic materials, is often the most sophisticated when properly understood. Invention 4. Peat and turf burning. Hypocausts needed fuel. In medieval northern Europe, wood was scarce. Forests cleared for farmland. Remaining timber too valuable to burn. Medieval peasants burned the earth itself. Peat. Peat is partially decayed plant matter from wetlands, forming over thousands of years. Dense, spongy, halfway between plants and coal. Energy density, 15 to 17 megajoules per kilogram. Nearly identical to dried wood. 3 advantages. First, abundance. Vast peatlands covered northern Europe, Ireland, Scotland, Netherlands, Germany, Scandinavia, England. Second, continuous formation. Peatlands produce 1 millimetre yearly. Medieval extraction was sustainable. Third, energy independence. 17th century Netherlands example. They consumed 25 million gigajoules of peat annually. Population 1.5 million equals 16.75 gigajoules per capita yearly. Today's global average, 76.6 gigajoules per capita. The Dutch used 1/4 of modern consumption. Critical advantage. Peat handled heating needs, so imported wood went to construction and shipbuilding. Higher economic returns. This helped Netherlands become a maritime power. Process. Cut peat blocks in spring and summer. Stacked to dry for weeks or months. Raw peat is 95% water. Dried peat burns slowly and steadily. With heat storage hypocausts, 1 load every few days. Calorific value, 9,200 to 9,800 BTUs per pound when dry. Lower sulfur than coal meant cleaner smoke for home heating. Today, we abandoned peat for fossil fuels. We lost local energy security. Medieval peasants walked to the bog and cut free fuel. No supply chains. no imports, no infrastructure dependence. Your modern home, completely dependent on power grids, gas pipelines, oil deliveries. Any disruption means immediate trouble. Medieval system, resilient, decentralized, sustainable. Invention 5. Root cellars. Warmth is half of survival. Food is the other half. In winter, nothing grows. Everything freezes. Modern solution, refrigeration running 24/7 on electricity. Medieval solution, the earth itself. Root cellars. 3 principles. Temperature. Earth below frostline maintains 32 to 40 degrees Fahrenheit year-round, just above freezing. Perfect storage. Frostline depth varies by climate. Northern regions, 4 to 6 feet. Medieval cellars went 6 to 8 feet deep, lined with stone for stability and thermal mass. Humidity. Vegetables need 85 to 95% relative humidity to prevent drying. Earth naturally provides this. Soil moisture. Stone walls wick moisture. High humidity without mold. Ventilation. 2 openings create natural convection. Cold air sinks through one. Warm stale air rises and exits the other. Prevents ethylene gas buildup that accelerates spoilage. Sophisticated designs use double-door airlocks. Enter first door. Close it. Then open second door. Prevents warm air disruption. Results. Carrots, turnips, beets, parsnips last 6 to 8 months. Potatoes, 6 to 8 months. Cabbage, 3 to 4 months. Winter squash and pumpkins, 6 to 8 months. Some cellars allowed continued growth. Transplant leeks or celery into cellar soil floor in autumn. They stay alive, not growing much, but providing fresh greens all winter. Compared to modern storage, refrigerator consumes electricity constantly. Power out for 1 day, everything spoils. Root cellar, 0 energy, no moving parts, no electronics, no infrastructure dependence. Medieval peasants built these into hillsides or under homes with trap doors. Communities sometimes shared cellars. 0 energy input, just checking stored food and removing spoilage. Medieval survival depended on this knowledge. Invention 6. Log cabin design. The building itself. How do you construct shelter that keeps heat in using only local materials? Medieval Northern Europeans developed the notched corner log cabin. Key principles. Massive wood walls. Logs 8 to 12 inches diameter or thicker. Enormous thermal mass. Walls absorb heat during day. Release slowly at night. Temperature fluctuations minimized. Notched corners. No nails or pegs. Interlocking cuts fit precisely. As logs dry and settle, they compress tighter. Wood expands and contracts with temperature, seating tighter into notches over time. Result: no gaps, no air leaks, almost perfectly sealed. Modern homes: dimensional lumber, drywall, thin walls, lots of seams. Air infiltration constant, cold drafts everywhere. Medieval log cabins, once chinked with moss or clay, remarkably airtight. Minimal openings, small windows, thick doors. Every opening is thermal liability. Heavy thatch roofs, 2 feet thick, excellent insulator, or sod roofs, birch bark waterproofing plus soil and grass. Massive thermal mass. 1 central hearth burning steadily was enough. Modern stick-built homes need constant heating operation. Log cabins required only periodic fuel addition. Which design survives power grid failure during polar vortex? Invention 7. Medieval chimneys and stone stoves. Finally, the hearth itself, the fire making everything possible. Early medieval homes used central fire pits. Smoke drifted up through roof gaps. Inefficient and dangerous. Smoke inhalation was a health problem. Heat escaped with smoke. By later medieval period, 2 innovations, the chimney and the masonry stove. The chimney directed smoke up and out through dedicated flues, eliminating interior smoke. But more importantly, it controlled airflow. Medieval chimneys used large stone or brick hoods, funneling smoke from open hearths. The hood created a chamber above the fire. This chamber allowed heat to radiate outward before smoke escaped. Hood acted as heat exchanger. Heat spread through masonry, radiating warmth for hours instead of rushing straight out. Benches or sleeping platforms built adjacent to chimney mass, Stone stayed warm long after fire died. The real breakthrough, masonry stoves. Kachelofen in German, Peksha in Russian. Developed 14th and 15th centuries, building on medieval principles. Not an open hearth, a chamber with small door for fuel. Fire burns hot inside, heating massive stone, brick or ceramic tile structure. Internal channels for smoke and hot gases through long winding path before exiting. Gases travel through channels, transferring heat to masonry. By exit, smoke is relatively cool. Almost all heat extracted and stored in stone. Result: build hot fire for 2 to 3 hours. Close damper. Masonry mass radiates warmth for 24 hours or more. One firing daily. Compare to open fireplace, most heat up chimney, or modern furnace, cycling constantly, burning fuel continuously. Medieval engineers understood thermal mass. Stone and ceramic store enormous heat. They designed systems capturing and holding fire heat for hours. We generate heat on demand, blow hot air around, but don't store efficiently. Medieval hearth. Sophisticated heat capture, storage and distribution system. Built from stone. No electricity. No complex controls. Just knowledge, skill and respect for keeping heat instead of wasting it. 7 technologies. 7 ways medieval peasants survived -40 degrees. Heat storage hypocaust. 5 days warmth from one fire. Lanolin wool generates heat when wet. Wattle and Daub matched 1995 insulation standards. Peat burning, local energy independence. Root cellars, 8-month storage, 0 electricity. Log cabins, thermal mass and perfect sealing. Masonry hearths, captured and held every degree. These weren't primitive. They were sophisticated physics, material science and engineering. Deep understanding of thermal dynamics, moisture management, resource efficiency. Modern technology gave us conveniences, but we lost resilience. Medieval systems didn't depend on supply chains, power grids, or fossil fuels. Local materials, passive physics, renewable resources. They worked for centuries, many buildings still standing, still functional. How many modern homes survive 500 years? How many keep you alive if power fails one winter week? The lesson isn't abandoning modern technology. It's remembering principles we may desperately need again. Climate change makes weather more extreme. Infrastructure ages. Energy systems strain. Stability we take for granted may not last. Maybe remember what worked. What kept people alive thousands of years before electricity. What worked in -40 winters with local materials, human knowledge, clever design. The medieval peasant had independence, resilience, knowledge that survival didn't depend on uncontrollable systems. Which technology surprised you most? Which should modern society rediscover? Drop a comment. If you enjoyed this, hit like. Subscribe for more practical wisdom from the past. Sometimes old ways weren't primitive, they were perfected. Thanks for watching.